This lesson will be on calculations with bond energies. You've seen before that a bond is a well. So here are the unbonded atoms. Let's make them have unpaired electrons, and here's the bonded atoms. That is typically a molecule, but it could be any kind of bond here. And now we're going to do mathematics with this. So here we have some numbers. Each bond, hydrogen bonded to hydrogen, oxygen bonded to hydrogen. Each bond has a particular energy associated with it, and that's the depth of the well. If it's a small number, this means it's a weak bond, easy to break. If it's a large number, that's a strong bond, hard to break. All right, so that's the general idea. Now let's look at some specific mathematics. Here's the first specific example. In state A, there are no bonds, so we're really saying this is an H dot, this is an H dot. These oxygens have 6 dots not bonded. And in that state, it's very high potential energy, which in this system is going to be 0. 0 is going to be the high point of energy because each bond that's formed lowers the potential energy. So here's an HH bond. From the table above, we see it's 430 kilojoules per mole. But it's best to think of that as a negative number because it lowered the potential energy by that much. Here's another negative 430. And here's a negative 500. And altogether, those add up to this value here. So that's the idea of mathematics here. Find the bonds, find their energies, find the total. So why don't you try state C? Try state C, calculate the bond energy. I'll show you the answer in a minute. All right, so what do I see here? I see an OO bond, that's 170, negative style. This is for 60 for the OH bonds. The HH bond we've already seen is 430, so these are all negative numbers. Add them up, and what do we get? This is negative 1520 kilojoules per mole. That's the total of those bond energies. You can see this is lower than state B, much lower than state A. And the last one is state D. This one's easy because it's just 460 times 4. There are 4 of them. You can see them 1, 2, 3, 4 of the OH bonds. That adds up to negative 1840 kilojoules per mole. All right, so that's the idea of the mathematics of bond energies. We can add them up to get the relative potential energy of different bonding states. The most stable state will be the lowest in potential energy. That's this one here. This one's the most stable. Water molecules are very stable, unlikely to be broken up, unlikely to change. Now we can use these relative potential energies to discuss energetics of a reaction, which is most important to chemists. There's a change here, change in bonding state. Every reaction is a change in bonding states. And that's all it is. No new atoms have been added. No atoms have been subtracted. Simply they're bonded to different partners. So we can analyze the energies. Where did we start at? This molecule H2O2 right here, is shown as a structure in the box. And you can see I put the bond energies next to it so we can calculate the total energy of that molecule relative to its atoms. And this is just an H2, so it has a bond, a covalent bond of 430 kilojoules per mole. So if we add all that together, 460, 460, 170, and 430, they're all negative numbers. So when we add that all up, we're starting at negative 1520 kilojoules per mole. That's the starting point. And how about the ending? That's 2 hydrogen molecules. So 2 of these right here, 2 of these, and 1 oxygen, 1 of these. You should see that's a total of 860 plus 500. We're ending at negative 1360 kilojoules per mole. All right. We can put those numbers into these spaces on the graph. Which is the lower number? Since they're negative values, the lower number is negative 1520 kilojoules per mole. And the higher number is negative 1360 kilojoules per mole. That may look backwards to you, but it's because these are negative numbers. These are wells. 1520 negative is way down in the well. So now we turn this into what's called an energy profile. We have done what it says here, filled in the relative energy values for reactants and products. And now the graph, this graph starts low. I'm trying to draw a flat line here saying that's the starting materials. Ends higher. So this is the energy state of the H2O2 plus H2. That particular bonding state is low in potential energy. This is the final product, higher in potential energy. And what's most important about this graph is what is the change? So the change in energy is symbolized with a triangle, which is delta, and an H, which you can think stands for heat. So this is delta H. That goes in the middle here. This is where it changes. Delta H. What is the change in this reaction? And this is where you do simple subtraction to find the difference between negative 1360 and negative 1520. In this case, there's a positive slope. You should see this as a positive slope. It's going uphill. So the sign here indicates the slope. Is it positive or negative? And the number is the difference, which is 160 kilojoules per mole. So this is a very important part of this reaction. You'll often see the delta H written as part of the equation. But the graph is the best way to symbolize what does it really mean. The products are higher in energy than the reactants. When that happens, the word that describes this is endothermic. This reaction requires an input of heat, specifically 160 kilojoules for each mole of hydrogen peroxide that we want to react. It's part of the equation. If you don't supply this heat energy, the reaction cannot occur. That's the meaning of the term endothermic.
Sometimes an energy profile slopes uphill, as you've seen here, but sometimes it slopes downhill. It starts with higher potential energy and ends with lower potential energy. That's an exothermic reaction.
So if you did number 3 correctly, or if you try number 3 now, you should find that's an exothermic reaction. Potential energy starts high and ends low, meaning heat will be produced.
So by graphing potential energy changes, you can determine the heat flow in a reaction.